Good morning, kids. I'm your physics teacher, Sridhar sir. In today's class, we'll be discussing about the atoms and X-rays in one shot. Is a class 12 syllabus, the last topic. Very simple and formula based, and one question for mains, and around one or two questions for the JEE Advanced, that one. Already you know atomic structure in the chemistry, the same ideas we'll be discussing here. So it's a dual advantage. Like if you study atomic physics here, it's going to help you in chemistry. It's a compulsory topic again. Everyone should prepare. Around 12 formulas are there. If you remember them, that is enough. And I can't give a very creative question here. It's a limited ideas. So just if you spend 1.5 hours, so short, you can manage this chapter very easily. Okay. So first, what is the methodology like? You have to watch what all I explain. Then afterwards, learning, not only just only seeing it, all the important concepts, ideas, what all I'm explaining, everything what happened one by one. Learn it, think on it when you're watching now. Then remember it, all the formulas, what all you come across, remember it. How you, after watching this, you'll forget re-watch it or relearn it. When you learn many number of times, 2, 3, 4, 5, 6, 7 times, then all the formulas will become memory. Then solve PYQ. When you're solving PYQ, you'll come to know how to use all these ideas, and that's what the confidence. The confidence for exam will come like this. There's no any magic method. Fine. So watch it, learn it, remember formulas, solve PYQ. You'll get exact platform so that you can manage most of the questions in JEE Mains or JEE Advanced. For JEE Advanced, again same, watch, learn, remember, solve different types of numerical. So can you suggest any good book for atomic physics? I think the Cengage textbook is covered wide number of numericals. Is a best preferable book for JEE Advanced. So for complete modern physics or total physics, that's what from my side. So you can prefer that book and practice as many, think on different types of numerical. If you check our lengthy video lectures, what I uploaded, there are also plenty of good questions are there. So watch them, you gain confidence. Okay, kids, like how to plan this atomic physics and X-rays. There's one more thing here. Atomic physics and X-rays, one shot. First, we'll discuss the different types of atomic models, like a Thomson's model, Rutherford model, and Bose model. Our syllabus is what only Bose model, and these are just only theoretical discussion, not in detail. Thomson and Rutherford model. First, we'll discuss theoretical, then come for Bose model, Bose postulates, then finding the expression for radius, speed, and energy of the atom in nth state when electron revolving in nth orbit, then hydrogen spectrum, excitation and de-excitation of atom, Rydberg constant, binding energy and ionization potential, then excitation of atom with electron, excitation atom with photon, if two excitation of atom with alpha particle, with neutron, with proton, with helium plus, lithium plus, or excitation of hydrogen atom by collision. There's a thing which will be very useful for exam point of view. Then recoil speed of the atom, then reduced mass concept, then hypothetical hydrogen like atoms based on Bose postulates. Then we'll go for X-ray. In X-rays again the Collis tube, continuous X-ray, line spectrum, and Moseley's law. These are all things are there. A few purely formula based. No need to bother. Not a conceptual. It's a purely formula based topic. As many formulas you daily read them, remember them, you will be in a better position in exam. Okay, kids. Okay, let me start with the explanation. Thomson's atomic model. So what Thomson he assumed that the atom is in spherical in shape and consists of positively charged in which electrons are embedded here. This is also called as a plum pudding model also. The magnitude of negative and positive charge is equal, making the atom electrically neutral. How much of positive charge, that much of electrons will be embedded here. The blue color one embedded, and the positive charge will get distributed throughout the atom, volume of the atom. Then, so this particular model successfully explains the thermionic emission. When you heat up, the electrons they start vibrating at one particular like a level of energy supplied, the electrons will get sufficient energy, they'll escape from this particular atom. Like that, the thermionic emission is what he was able to explain using J. Thomson's model. What are the limitations? Like arrangement of electrons. So how come this electron like it can be captured by the positive charge because they are at rest, no? Then this electron can be captured by the positive charge. So the stability of atom was a problem, and the position of electrons also. Where do electrons must be located? Randomly, so he could not explain. Uh, Next, Rutherford was able to describe the nucleus. Here, why the nucleus? Nucleus spread throughout the atom. But Rutherford experiment was something totally different. The nucleus was present, highly concentrated at the center of the atom, that one. Whereas here, the nucleus is present throughout the atom. So this was the thing. Scattering of alpha particle. Next again. So when you send alpha particle, they'll get scattered. Here, I think we'll not obey that one. And moreover, it could not explain the hydrogen spectrum. So these are the problems with the Thomson's model. Some theoretical questions can be asked in JEE. That's what I'm just giving brief idea. Next, Rutherford atomic model. There's a gold foil, thin gold foil or sheet made up of gold. Here source of alpha particle as like a source which will emit the alpha particle. The alpha particles are accelerated using electric field and they'll be focused using magnetic field. A beam of alpha particles will come. They'll come and they'll be striking this sheet made up of gold. What we see that the alpha particles get deflected. Some of the alpha particles get deflected by almost 180 degree here. Some and most of them will pass as if nothing is present and some will get deflected. So what is the deflection? The deflection of between 0 to 180 degree, and most of the alpha particles they'll have deflection of 0 degree, means they'll get undeflected. Most of the particles are undeflected. This is a fluorescent screen. Now, what do you mean by fluorescent? When fast moving alpha particle, when fast moving particle, if it strikes a screen, the kinetic energy will be lost due to collision and they'll be converted into heat, and the particular fluorescent, usually phosphorus screen will be there. The phosphorus particular material, when it suddenly gets energy, it will produce the illumination, some sort of fluorescent, what we can call it. So a phosphorus screen is circular, like a fluorescent screen made up of phosphorus and the zinc, potassium, combination of that will be there. So where like I will get the fluorescence, there nothing but the alpha particles will be striking. Most of the fluorescence is noticed here. Then as you move away, the fluorescence will decrease. So means most of the alpha particles are striking in this region, because we can't visualize alpha particle. Only through fluorescence we are able to tell that as here the alpha particles will be more. So here we can see more fluorescence here. What do you mean by fluorescence? Illumination or sparkles of light. During Deepavali festival, crackers. So when you burst some crackers, what all you get, that fire, no? That's called fluorescence. Or matchstick. When you lit the matchstick, we'll get the fluorescence. That's what we are discussing here. Then what is the basic condition here? So all the alpha particles, all the positive charge and mass number of atom are very small part of that. With this you are able to conclude that the total charge of the atom, we call that as nucleus, will be concentrated at the center of the nucleus. And radius of this nucleus will be of order 10 to the power of -3 meter. So now most of the atom will be empty. And what about the electrons? The electrons will be revolving around it. And what is the large deflection? This particular thing, you can see this deflection. Why this deflection? Because of Coulomb's repulsive force. Because alpha particle will be positive, the nucleus will be positive. So only few will get deflected. And here you can see that one. And most of them will pass through as if like an empty space here. So the large deflection of the particles the deflection is due to Coulomb force here. Here roughly I'm showing it. So here some of the electron, what happen, will alpha particle will get deflected back. Here the condition like this, this alpha particle. And this is the nucleus. This will be fixed here. And they're coming from far away. This projectile, it will approach the same alpha particle. When it approaches the closest approach is what we'll call it. Same nucleus. This will be fixed here. And it will come to rest. Or the instantaneous rest. This is called like a closest approach. Then how to calculate this one? Initial kinetic energy, K alpha, plus interaction potential energy. Interaction potential energy will be charge of alpha particle, Q alpha, charge of nucleus, ZE, charge of alpha particle, 2E, by 4 pi epsilon naught infinity, far away, no? Equal to finally comes to rest, 2E ZE 4 pi epsilon naught x here. So kinetic energy of alpha particle is equal to 2ZE square 4 pi epsilon naught x. This is the distance of closest approach. Okay, this one twice they asked in JEE means distance of closest approach. It all depends on the kinetic energy. So this is what happens. They'll get deflected by 180 degree. So with this, what we can conclude here, according to the Thomson's model, Rutherford model, there will be like a positive charge centered at the atom, and most of the atom is empty, and the electrons will be revolving around it. Now, okay, he proposed this atomic model. So what the problem is like then he said that this electrons will be revolving, will not be at rest, will be revolving in the sense then according to the electromagnetic electrodynamics, accelerating charge particle, because as it is moving in a circular path, there will be an centripetal force will be acting on it, and it will have acceleration, centripetal acceleration. So any accelerating charge particle, due to change in direction of motion, there is an acceleration. So it should give out radiation. So continuously it will give out the radiation. Then the stability of atom itself is a problem. And one fine day the electron will fall into the nucleus. But we know atom is a stable. So the Rutherford could not explain. The Rutherford could not explain. And according to this, the spectrum emitted will be continuous. But we know hydrogen spectrum is a line spectrum. But according to this, continuous spectrum. So the line spectrum, there's a continuous spectrum. But we know there's hydrogen spectrum. So Rutherford, he said it's continuous spectrum. So therefore, here this Rutherford atomic model failed to explain the hydrogen spectrum and failed to explain the stability of the atom. And there's the basic problem with this one. So to overcome this, what happened? The Bohr proposed a new atomic structure called as a Bohr's atomic model. Before that, we will discuss about the some related to the deflection. There's a part of syllabus can be asked in JEE means. I don't know how you remember. You have to remember this. What is theta? Theta is the deflection angle. This theta. And for different particular alpha particle, the deflection angle will be different here. There's a deviation. Okay, fine. Positive charge of the target atom, mass of the alpha particle, incident speed of the alpha particle. Then theta is the scattering angle. And this particular is the deviation. I'll better call this. We'll do one thing. This is scattering angle. There's a formula for scattering angle. So this particular thing also you have to remember it. Will all particles, all incident alpha particles will deviate by 180 degree? No, only one. Out of for every 8,000, only one what will happen will get deviated. The remaining all will just pass through it. There's a scattering part of syllabus. You have to remember this formula. Further, this Rutherford, he wanted to explain like this: the two electron atom, and this atom contains two electrons. Who will provide the how it will get balanced here? So according to him, this Fn minus Fn equal to mv square r. What is Fn? Force of attraction between the nucleus and the charged electron, 4 pi epsilon naught r square, minus F12, the force of repulsive force between the electrons, so 4 pi epsilon naught 2r whole square. Like this he wanted to explain, but still not possible. Then like this we can get the relation between the radius r. So here also again the same problem. The exciting charge particle should radiate, its kinetic energy should decrease, and one fine day it will fall into the nucleus. But it is also the same problem. The stability was a problem. Okay, fine. We'll discuss the Bohr's atomic model. We'll start with the Bohr's postulates. According to the Bohr's postulate, the electrons revolve in specific orbit. Electrons are not free to move around the nucleus. Instead, they occupy the specific circular pass orbit or shells. They'll move in a specific circular orbit of radius r, 4 r, 9 r, 16 r. Specific word. This is very important. Quantized energy levels. Each orbit corresponds to a specific fixed energy level, and electrons can only exist in these orbits. Where we can search the orbits, where we can find the electron either in the first orbit, second orbit, third orbit, fourth, fifth, sixth, seventh. In between here, not possible. It has to be in the orbit only. No energy emission while in the orbit. As long as the electron remains in a specific orbit, when it is revolving in this orbit, it will not emit any energy. Neither absorbs nor emit energy, maintaining a stable state. Means if electron revolving in the circular orbit, though it is accelerating, it will not emit. Energy transition. Electrons can move between orbits by absorbing or emitting energy, but only in specific quantized amounts. The electron can move from lower state to higher state, or can move from higher to lower state. If electron absorbs energy, it will move to higher state. If electron gives out energy, it will move to the lower state. Angular momentum quantization. The angular momentum of electron in orbit is quantized. Means what is the Bohr's postulates? There is a Bohr's mvr is equal to nh by 2 pi. The angular momentum of the revolving electron is quantized, where h is the Planck's constant, and will take value 1, 2, 3, 4, and so on. The specific orbits are also called as stationary orbits. These are called as stationary orbits. Now, if an electron moves from higher to lower orbit, it will give out the energy. If electron moves from lower to higher orbit, it will absorb energy. If it absorbs energy, it will move from higher to lower orbit. If it releases, it will give out the energy. That if it moves from higher to lower orbit, it will give out the energy. This is an electron. It is revolving in a lower orbit in the ground state. It absorbs photon. It will jump to excited state. It will stay here for a small interval of time. Again, it will come back to the lower state. Then you give out the photon. By giving out photon, again it will come back to the original state. So here roughly will indicate like this. The electron, it is in n equal to 1. It will absorb photon. It will jump to the higher state. Again from n equal to 2, it will come back to the ground state. It will give out the photon. Photon, emission of energy or emission of photon. Here absorption of photon. This is one basic idea. This is the nucleus. This part is the nucleus. This is a revolving electron. The electron here, it will stay in the excited state for what duration of time means? 10 to the power of 8 seconds. For this much of interval of time, the electron will stay in the excited state. Again, it will come back. It will not stay n equal to. For what time it will be there at n equal to excited state? For 10 to the power of minus 8 seconds. Again, it will come back to the n equal to 1. This is a basic idea. Very, very important for us. There is a standard data which you should remember. So once again I repeat, the electron will stay in the excited state for an interval of time 10 to the power of minus 8 seconds before making transition to the lower state. This is the lower state, this is the upper state. Highest, this is the lower state, this is the highest state. This is the electron. It is revolving in the nucleus. This nucleus is proton. We are discussing this for hydrogen atom. This electron is revolving in a circular orbit of radius r. The electrostatic attractive force will provide the required centripetal force. This electrostatic attractive will provide the required centripetal force. According to Bohr's postulate, the angular momentum is quantized, which is equal to nh by 2 pi, where n is integral multiple, n equal to 1, 2, 3, 4 values it will take. Then angular momentum of revolving particle should be mvr. Solving 1I2, we'll get expression for the radius of the nth Bohr orbiter. This will be the expression for radius of the nth Bohr orbit. Then if you substitute this, z equal to 1, further simplification, this Rn equal to n square A naught by Z. This will be our generalized formula. For hydrogen atom, Z will become equal to 1. Then what is A naught? A naught is like a Bohr's orbit, n equal to 1, the Bohr orbit, where the value is 0.53. Then everything will be in angstroms. This everything you should remember, very, very important. This is the expression for radius of the nth Bohr orbit. If the electron is there in nth orbit, this is the expression for the radius. N is the orbit, Z is the type of hydrogen atom. Hydrogen atom Z equal to 1. If the helium plus Z equal to, if lithium double plus Z equal to 3. Okay, fine. Similarly, we'll now substituting this value of R, the value of R in this equation, expression for speed, we'll get expression for the speed of electron in the nth Bohr orbit. Further simplification of this will be, okay, here only, let me write equation. Next, the speed of electron in the nth Bohr orbit is given by ZC by 137N. I think for exams, this will be very, very useful. These values will be very, very useful. C will be 3 into 10 to the power of 8. This everything speed will be in terms of meter per second. That is the hydrogen-like atoms. Then N is the quantum number. N equal to N will take value 1, 2, 3, 4, 5, and so on. These are the basic conditions. Next, similarly, we'll go for the. We know the kinetic energy equal to half mv square. We'll substitute the value of v. I'll get the kinetic energy. Similarly, the potential energy, substituting the value of r. The sum of potential plus kinetic will end up the equation like this. This will become Rn value. Already we know. This should be equal to Rn equal to n square A naught by Z. Already we know this value. Now the energy equation is given by this one. Z square RSC by n square minus of, where R is the radius of the nth Bohr orbit. Okay, sorry, there is a Rydberg constant, where there is a capital R is a Rydberg constant. The energy equation we write in terms 13.6 Z square n square by E, or this particular formula. This is the expression for energy, and the total energy should be equal to sum of potential plus kinetic. Okay, fine. Potential will be negative as a bounded system. Kinetic energy will be positive. Okay, fine. So these are the formulas which you have to remember. Very, very useful for you. The kinetic energy, if you already we have solved it. Sir, what is the relation between the potential and kinetic energy? The kinetic energy will be twice the K equal to mod of E mod of U by 2. This is one basic relationship between the potential energy and the kinetic energy. And this will be valid for the conservative forces. And these equations you have to remember. One, there is a Rydberg constant, there is energy equation, the radius of nth Bohr orbit, then expression for speed. Okay, fine. So this is the, we'll take the next condition. Now, if the electron is in the first orbit, this is first orbit, n equal to 1, n equal to, n equal to. If electron in the first orbit absorb the photon, it will get excited. It will go to the higher orbit. Okay, fine. Then same electron. So here again n equal to 2. Now, if the electron is in second orbit, if it absorbs photon, it will jump to the higher orbit, n equal to 3. What do you mean by emission? If the electron moves from n equal to 3, this is n equal to 1. It jumps from higher orbit, excited state n equal to 3 to 1. Then it's called like an emission. It will emit a photon of wavelength. Similarly, the electron can make transition from n equal to 3 to 2. It will make a transition. This is the photon. This will be lambda 32. The wavelength of this photon will be lambda 31. So how to predict the wavelength of this emitted photon? This particular phenomena is called as excitation. This is called as de-excitation. When atom absorbs photon and its energy increases, called as excitation. When atoms jump from higher state, when the electron in an atom jumps from higher to lower state, called as de-excitation. In de-excitation, it will give out the photon. Then how to calculate the wavelength of photon? The energy of the photon, this energy of the photon is equal to EF minus EI. We know EF value equal to, substituting this one, the energy of photon should be equal to HF. EF in terms of EI we are expressing. So then 1 by lambda, E1 equal to, in terms of the Rydberg constant, EF equal to RHC. Everything the simplified will be 1 by lambda equal to R by NF square minus NI square. Final state to initial state. This will be we'll be using this formula to find out the wavelength of the emitted photon. Now, if an atom absorbs the photon, it will get excited, and it will stay in the excited state. For what interval of time it will stay here? 10 to the power of minus 8 seconds. And again it will get de-excited. Now we'll directly get into the hydrogen spectrum. Very, very important. Now the electron got excited. A photon is incident. And it is at highest state. The electron makes a transition from n equal to 2 to n equal to 1. What are these? These are energy layers. So from how these equations you brought it, I'll be using this formula. En equal to minus 13.6 electron volt Z square by n square. Z equal to 13.6 electron volt z square by n square. This z equal to 1. Then here, if the electron makes it put n equal to 1, put z equal to 1, this hydrogen atom. Put z equal to 1, put n equal to 1, 2, 3, 4, 5, 6, we'll get the energy levels. This is called like a ground state. This is called like a first excited state. Second excited state. Third excited state. Like this will be fourth excited state. N equal to 2 will call excited state. So all these are called as excited states. Okay, fine. Now this particular line, the wavelength of the photon, lambda to 1. When electron makes a transition from n equal to n equal to 1, this will become first line of Lyman series. When electron makes a transition from n equal to 3 to 1, second line of Lyman series. Third line, fourth line. Similarly, if electron from higher excited state makes a transition to the lower state n equal to 2, this will produce the Balmer series. I'll repeat once again. If the electron makes a transition from excited states to the ground state, Lyman series. If electron makes if it makes a transition from excited state to the first excited state or n equal to 2, Balmer series. If electron makes a transition from higher excited states to second excited state or n equal to 3, Paston. If electron makes a transition from higher excited state to third excited state or n equal to 4, bracket P fund. Like this, we'll get the hydrogen spectrum. It's a line spectrum. You don't get photons of all wavelength. Only specific wavelength are produced here. Lyman series. So here ultraviolet region, Balmer series visible spectrum, Paston series infrared, bracket series infrared region. So next again the P fund will be infrared region. Then how to calculate the wavelength of any particular line? You can use this particular formula. For Lyman series, what is the final state? Final state will be n equal to 1. And what about Ni? Ni will be 2, 3, 4. For Paston series, for Lyman series, like this one. For Balmer series, n equal to 2 will be the initial, 2 will be the final, n equal to I will be the initial state. It will be 3, 4, 5, 6. I think I missed that particular thing. I'll write it here. For Balmer series, 1 by lambda equal to R. What about n? N will start from n equal to 3, 4, 5, 6. Like this, you can find out the wavelength of the line in the hydrogen spectrum. Of all the wavelengths, you can find out. Lyman series, the final state will be 1. Initial state will be 2, 3, 4. The Balmer series, the final value NF will be 2. The initial will be n equal to 3, 4, 5, 6. Next, after Balmer Paston, final state n equal to 3. The initial state will be n equal to 4, 5, 6, 7. Like this, we can find out the wavelength of any line in the hydrogen spectrum. Okay, agree this. So this data you have to remember, very, very important. Next again, here the same thing in terms of the atomic structure I am discussing. This is a nucleus. So here the Lyman series. If the electron makes a transition from higher state to the ground state, then we'll get the Lyman series. If the electrons will make transition from higher excited states to the n equal to 2, then we'll get the Balmer series. If the electron makes a transition from higher excited state to n equal to 3, we'll get the Paston. Similarly, same thing. What do you mean by once again excitation? If an electron absorbs the photon, the electron will jump to the higher state. Then again it will stay there for 10 to the power of minus 8 seconds. Again will return back to the ground state. This will become de-excitation. Next question comes, what all the wavelength for the Lyman series? I'm just showing this one. So for wavelength for the Lyman series, this will be the formula. N equal to 2, 3, 4, 5. This is for Lyman series. So I'll substitute here n equal to, I'll solve it, I'll get 121.5 nanometer. This is called like a first line of Lyman series. This is called like a second line of Lyman series. This is called like a third line of Lyman series. This is called Balmer. So how to get the Balmer series transition? What is the formula? 1 by lambda equal to R. And so on. Okay, this will be the no. This will be the first line of Balmer series. We'll call this as first line or H alpha. Second line of Balmer series. Third line of Balmer series. H alpha, H beta, H gamma. We have given some specific name for also. Very important. Like this, we'll calculate the wavelength. Substitute all this. Rydberg constant value substitute. Then we'll get the wavelength here. What is the value of R? The value of R, you have to substitute this much. All this will be in the nanometer. The Balmer series also will be nanometer, or you can express in angstroms. These are the Balmer series. So here when electron absorbs the energy to jump to n equals 6, from n is equal to 6 to 5 to 2, 4 to 3 to 2 will become the Balmer series. And these are the wavelength. Okay, you have to roughly remember the data will help you a lot. There's a complete hydrogen spectrum table I brought it up, which you have to memorize. There's a energy level diagram. This is called as ground state, and this is the first excited state. Energy in the first ground state will be minus 13.6 electron volt. In the first excited minus 3.4, second 1.5, 0.8. Like this. This is called as second excited, third excited. So now initial state 2, 3, 4, 5, and 6. So this will be the series. This will become the Balmer series. Final state, the wavelength, series limit, UV region. So this particular thing, we'll call this as Lyman series. Okay, remember like this. This is a Lyman series. How to calculate the Ni will become equal to 2, 3, 4, 5, 6. Same thing I'm repeating. First member, second member. What do you mean by first member? The wavelength of the first line. N equal to 2 to 1 is called as the first line. What do you mean by series limit? When this will become equal to infinity. From infinity to 1. It makes from infinity to n equal to 1. Then this will become lambda equal to 1 by r. Then what is the wavelength? 911 Armstrong units. Then maximum wavelength. This is series limit. Then maximum wavelength. Maximum wavelength will be from 2 to 1. 2 to 1 substitute 2 here will become lambda is equal to the wavelength only that we are the symbol got here. The wavelength maximum wavelength is given by 4 by 3r, and in terms of angstroms 121 Armstrong. This is the lambda itself. Okay, now for the Lyman series, the first series limit limit will be n equal to infinity, put ni equal to infinity, lambda equal to 1 by r, and the wavelength is this much. Next, maximum wavelength will be from 2 to 1, the second line. will be lambda equal to 4 by 3r. This will lie in the ultraviolet region. Next again this will become the Balmer series. NF final state will be NF equal to 2. Ni will be 3, 4, 5, 6, 7. First member will be 3 to 2. Second member will be from 4 to 2. Here it will be like this will become first member of Balmer series. This will become second member. Then what about the wavelength? Series limit. Series limit will be from infinity to 2. Put n equal to infinity will become lambda equal to 4 by r. This is the shortest wavelength. Series limit. Maximum wavelength will be from 3 to 2. Then there will be 36 by 5r. 6563 angstroms approximately. Similarly, this will become Paston series. And this will be bracket series. This will be P-Fund series. So like this we are and these are regions. Lyman, ultraviolet, Balmer visible, infrared will be Paston bracket, and for infrared will be P-Fund. And like this we can calculate the first member. This called like a first member, this called like a second member, this called a third member. Here first line of Balmer series, second line of Balmer series, third line of Balmer series. Series limit will be from infinity to this point, from highest n equal to infinity to this, called like a series limit. Maximum wavelength will be this adjacent transition. There's a data which you remember. Of all this, these formulas are very important. This is about the hydrogen spectrum. You are supposed to remember, very very useful for you. Once again, I am repeating. There's an incident photon, absorbed photon absorbed. Where hydrogen atom, it is in the ground state. When hydrogen atom absorb the photon, it will get excited to highest state. Then again, for what time it will be there? 10 to the power of minus 8 seconds, the electron will stay in the excited state. Then again, will undergo de-excitation. De-excitation, photon emitted. Your entire problem solving is this idea. Very, very important. I'm repeating this third time. This is called like a excitation. This is called like a de-excitation. When atom de-excites, it will give out the photon. Okay, agreed. When it de-excites, it will give out the photon or the lines, and that is not nothing but the hydrogen spectrum. Once again, I am bringing here. Now there is an incident photon. Hydrogen atom is in ground state, will get excited. For what time it will be there? It will be present here for an interval of time 10 to the power of minus 8. Again it will undergo de-excitation. If de-excites, it will emit. And it will return back to the ground state. This is n equal to 2, n equal to 1. Okay, this diagram. Okay, no? Then again electron will return back to the same ground state. This is called de-excitation. Your entire problem solving is this concept only. This you watch it 2, 3, 4, 5 times. Digest it, understand, remember. Based on this is what all our atomic physics. Excitation means you should know what is the de-excitation. Excitation, the atom absorbs photon, moves to the higher state. De-excitation, the atom moves from higher to lower state and will give out the photon. No, this electron which is moving with a kinetic energy 10.2 electron volt. This is the hydrogen atom. With the hydrogen atom, it is in ground state. In ground state. This electron collides, then it will be this whole energy will be absorbed by it. So with what is the energy of the incident electron? 10.2 electron volt will be absorbed by the hydrogen atom and the electron will get excited. Then after this electron will supply this energy, it will come to rest. This electron will come to rest. The hydrogen atom will get excited. Then it will undergo de-excitation. Now this hydrogen atom will get excited, will undergo de-excitation. Again the electron will jump back to the n equal to 1 state and it will give out the photon. So now atom, can it accept energy from the electron? Yes, it is. How much of energy needed by the electron to excite hydrogen atom? It is around 10.2 electron volt. What happens if it comes with energy less than 10.2 electron volt? It will not absorb, because what is the minimum energy needed to excite hydrogen atom? It is around 10.2 electron volt. Now the electron is incident with 10 electron volt. The hydrogen atom, how much minimum needed? The minimum needed is how much? 10.2 electron volt. But how much of incident energy? The incident electron is having energy 10 electron. It cannot absorb it. It will just collide elastically and will rebound with the same speed. So here we can call it as like some elastic collision. It will rebound with the same speed and there won't be any, this hydrogen atom will not get excited or de-excited. What happens if it comes with energy more than that? One more idea. What is the incident electron now? It comes with energy 11 electron volt, but how much minimum energy needed to excite hydrogen atom? 10.2 electron volt. This particular collision will be an elastic collision. Collision will take place. How much needed for excitation? 10.2 electron volt. So it will give the remaining 0.8 electron volt. It will rebound, and where this electron will not be here. This electron will get excited. The hydrogen atom will get excited. And what is the state of this? Will be in the second excited state. Second excited state, how much it will be? 3.4 electron volt. The hydrogen atom will jump to the second excited state and it will stay there for 10 to the power of minus 8 seconds. Again the electron will jump back to the n equal to 1. So look at this. So what is the type of collision now? We can call this as inelastic collision. Earlier it was elastic collision. Inelastic collision. This is one basic idea with the electron. Now we'll take this next, the photon. Next is the photon. If it is incident on hydrogen atom, which is in the ground state, let the energy of the photon is such that it's having wavelength 1 to 1.5 Armstrong units. Then the hydrogen atom will absorb this photon, because this wavelength of photon is corresponding to the delta E equal to SC by lambda. When you substitute this energy corresponds for 10.2 electron volt. So therefore the hydrogen atom will get excited, the electron will go to the n equal to second state, or the hydrogen atom will be in the first excited state. It will stay here for 10 to the power of minus 8 seconds and will de-excite and will give out the same photon. Then if the hydrogen atom is in ground state, if the wavelength of incident photon is 1025 Armstrongs or 1.025 10 to the power of minus 7 meter, then the hydrogen atom will absorb this photon, will get excited to n equal to 3. And it will be in the second excited state. When it de-excites, it will give out the same photon. I'll put it here. Now this hydrogen atom, it will absorb the incident photon. 1 to 5 will get excited. The how much of time? This time interval will be 10 to the power of minus 8 seconds. Afterwards, it will undergo de-excitation, will give out the same photon. Similarly, if the photon incident is having wavelength 1025 Armstrongs and that should be equal to delta E, the difference of these two, then the hydrogen atom will get excited to the second excited state, will de-excite and will again release out the same absorbed photon. So therefore, when the hydrogen atom will get excited due to incident photon, only if the energy corresponds for the difference in energy level of the energy level diagram. It cannot absorb all the photons. Only the photons which will carry energy equal to the difference in energy level, only it can undergo the transition. Whereas electron not like that. If the electron comes with energy, anything more than 10.2 electron volt will be absorbed and the hydrogen will undergo transition. But for photon, not like that. It should come with specific energy only, and how much that energy should be equal to delta E. Then only open, it will get excited. The hydrogen atom will get excited. Then the photon will be absorbed, and after de-excitation, again it will give out the same photon. And there's one basic condition happens with the incident photon. Okay, now there's a next very important thing. So this is the incident particle. It can be neutron, proton, hydrogen atom, or it can be alpha particle. This one will be the target atom, which has to be excited, to the higher level. These are the conditions we are assuming. Now, what will be the minimum kinetic energy of the incident particle so that it can excite this atom? This one is atom. There's a incident particle. Then the minimum kinetic energy is given by delta E, the energy needed to excite. This atom can go to n equal to 2, n equal to 3, 4, 5, anything. Calculate the delta E, 1 plus mass of incident particle by mass of the target atom. This will call as target atom. There's a one generalized formula, try to remember. So what all energy needed? It has to carry energy so that it will excite, and also finally what when both the incident particle and the target atom should move with a common velocity, so it should come out with both the energies here. So this minimum kinetic energy, what actually it is equal to delta E plus kcm. There's a concept I explained in the channel available. Directly I'm writing the formula as it is one shot instead of derivation, this one. So let's start with the neutron. Let the neutron excite the hydrogen atom. What conditions are needed? What will be the minimum kinetic energy of the incident neutron so that it will excite hydrogen atom to the n equal to 2. So for this I should use the formula delta E 1 plus incident particle by that of the hydrogen atom. What is minimum energy needed to excite 10.2 electron volt? Mass of neutron is almost equal to mass of hydrogen atom. Okay, this is mass of neutron by mass of hydrogen atom. This will become 1 by 1. This will be 20.4 electron volt. If it comes with energy equal to this, okay, it will excite it. If it comes with energy less than this, just it may undergo simple collision. So what is the kinetic energy here? 20.4 electron volt. This is the first case. Second case will decrease. If it comes with the energy 20 electron volt, what will happen? It will undergo just elastic collision. The neutron comes with a kinetic energy equal to 20 electron volt. It will collide elastically. We should not say anything like that, just collides elastically. Then the kinetic energy of the neutron will be given to the hydrogen atom, and the hydrogen atom starts moving with 20 electron volt, and it will be there in the ground state only. There won't be any excitation. This is what happens with the 20 electron volt. Now if it comes with more than this, we'll see what conditions will come. If the neutron comes with energy more than the minimum kinetic energy needed to excite, the hydrogen atom will get excited, and the neutron and the hydrogen atom will not get stuck. They'll be moving with a different speed. Then here the energy equation will write like this: Kn equal to, what is this? This should be equal to Kn, the kinetic energy of the incident particle. This should be equal to K1 plus K2 plus delta E. A part of this incident kinetic energy will be utilized to excite the hydrogen atom. Okay, now K1, K2 are unknown, so we can apply the conservation of linear momentum also. According to conservation of momentum, 2 times of Mn Kn equal to 2 times of Mh Kh or K2 plus 2 times of Mn K1. Since Mn equal to Mh, root kn equal to root k2 plus root k1. So solving these two equations will get the required answer. If it comes with energy more than this, okay, it will get excited, but they'll not get stuck, and they'll be moving with a different kinetic energy. So there's one very general idea now. Try to remember. If alpha particle is incident on a hydrogen atom, okay, we have to, what is the minimum kinetic energy of alpha particle needed to excite the hydrogen atom? Again, the formula will be K alpha equal to delta E 1 plus mass of incident particle, mass of hydrogen atom. Delta E 10.2 electron volt. Mass of alpha particle 4 times mass of hydrogen atom will be 5. This will be 51 electron volt, and both will be moving with a common velocity. Okay, fine. If it is electron comes, then mass of electron will be negligible, so just equal to 10.2 electron volt. Initially I discussed the first case. So how much of energy needed? 51 electron volt. If it comes with energy more than that, then the alpha particle and the hydrogen atom will lose contact. If it comes with energy less than this, a collision will occur. Just mere collision will take place, and they'll be moving with a different speed. Next situation, if the incident alpha particle comes with energy less than minimum kinetic energy to excite, they'll undergo collision. Then K alpha equal to K1 plus K2. Then applying conservation of linear momentum. 2m alpha K alpha equal to 2m alpha K1 2mh K2. Since m alpha equal to 4 mh, so this will become K alpha is equal to here K1. mh will become 4 alpha. This will become 2 root K2. Then solving these two will get the K1, K2. And the hydrogen atom will not get excited. Just they'll undergo some collisions. This is about any particle. So there's one generalized formula. Kinetic energy of incident particle equal to delta E 1 plus mass of incident plus mass of the atom. Mass of incident particle by mass of the atom. This is a generalized formula which you should remember. Next we have the situation. This is a helium atom. There's a neutron incident on helium atom, collides. After collision, the helium atom gets excited, and the neutron and the helium atom will be moving with a kinetic energy K1, K2, and they'll get deflected. So how this particular we have to discuss that one here. Now, what all the energy supplied? What is this energy supplied? What all the energy supplied by the neutron? It should be equal to kinetic energy of the neutron and the helium after collision plus excitation. You can see helium atom was in ground state. Now it got excited. It is in excited state. So the kinetic energy supplied by that should be equal to K1 plus K2 plus delta E. How to calculate delta E? Energy of the helium atom in the first state, E1, is equal to minus 13.6 electron volt. Z square will be 2. Helium plus atom will be n square. This will be 1 square. This will be minus 54.4 electron volt. What is the energy in the next orbit will be minus 13.6 electron volt. 2 square will be in the excited orbit. This will become minus 13.6 electron volt. And the difference of this is what? The delta E. Okay, fine. Now, how to solve this one? Because we need K1, K2. These are unknown things. Applying conservation of momentum along x-axis. 2mn K0 equal to 2mn K1 cos theta 1 plus mass of helium atom into K2 cos theta 2. Conservation of momentum along y-axis. Initial momentum is 0. Final momentum will be 2mn k1 sine theta 1 . Solving this, we'll get some information of theta 1, theta 2. If they give, we can get the k1, k2. There's one basic general thinking what you should develop. Okay, theta 1, theta 2, it will be given for us. There's a two-dimensional collision like this, you have to remember. Now, if n equal to 3 becomes again k1, k2, theta 1, theta 2, they'll get deflected. Even theta 1 can be 90 also. Theta 1 can be 90. Substitute theta 1 90. And then solve the problem. Possible, even possible. After collision, the neutron will get deflected normally. This is also possible. Even such a type of collision also will take place. Now this hydrogen atom is in excited state, so where it is n equal to 4, it will undergo de-excitation. It will undergo de-excitation, it will come to the ground state. Meanwhile, it will emit the photon. Then, because of this emitted photon, the atom will recoil. Then, from the conservation of momentum, the momentum of photon should be equal to momentum of atom. What is the momentum of photon? The momentum of photon should be equal to h by lambda. Momentum of atom will be mass of hydrogen atom, velocity of hydrogen atom. Then what is the wavelength of photon emitted from the Rydberg constant? 1 by lambda r equal to 1 by 1 square 1 by 4 square. From where to where the transition takes place from n equal to 4 to n equal to 1. So this will be 1 by lambda equal to r1 minus 1 by 16. 16 by 15r. So substitute this. H equal to 16 by 15r equal to mass of hydrogen atom into speed of hydrogen atom. These are the above some generalized formula I kept it. So substituting this, VH, recoil speed of the hydrogen atom will be 15 RH by 16 mH. Oh, there's one generalized formula which you can remember. So what is the generalized formula? I'll generate formula here. This should be equal to VH equal to Rydberg constant by RH by mH by 1 by Ni square Nf square Ni square. Okay, like this. This is the recoil speed of the atom, hydrogen atom. Any atom, mass of that atom you substitute here. And what is the transition? If it is some helium, then you have to adjust the Z also. The Z will come here. If some other helium atom, the Z will come. Or lithium double, helium plus, lithium double plus, the value of Z will come. Okay, this is a generalized formula you have to remember. Why it will recoil? Because the momentum, the photon will be associated with momentum. So as some momentum is generated towards left, so therefore the atom should recoil. It will move with a very less speed that is given by this particular formula. For any transition, this will become generalized one. So what is Ni? This will be Ni. This will be Nf. Okay, kids. This is a hydrogen atom. This is a lithium double plus atom. Lithium double plus atom. where it contains 3 electrons, 2 electrons are removed. Lithium double plus it is. It is a test. Then both are in ground state. With what kind of change the hydrogen atom must come so that it should excite the hydrogen atom to n equal to 2 and the lithium atom to n equal to 3. Then we can use the formula. What's the minimum kind of change I'm asking? So what should be the formula? K naught equal to delta E 1 plus mass of incident particle, hydrogen atom, mass of the target atom, lithium atom. What is delta E? Delta E we have to calculate like this. Delta E for hydrogen atom, it will be difference in energy. How to calculate the excitation energy? The hydrogen atom should move from first excited state to second excited state. Then there is the energy one. Okay. Then the lithium double plus ion, it should be excited. It is in ground state. It should be excited to third state. Then there is a formula. What is the Z for lithium? For lithium, Z will be 3. For hydrogen atom, Z will be 1. I am using formula En equal to minus 13.6 electron volt Z square by N square. Substitute all the values. We'll get the energy in the state. This what delta E we are going to substitute. Mass of lithium atom. Mass of lithium atom will be 7 times that of the hydrogen atom. We'll get the minimum kinetic energy. If the kinetic energy of the hydrogen atom is greater than this, then both will not move with a common velocity. In fact, they'll be moving with a different speed, v1 and v2. If it comes with energy less than this, they may not undergo excitation. Okay. So almost all the ideas I gave, you have to remember, understand, and you have to remember it. This is what atomic physics. Next week, in most of the in hydrogen atom, we'll neglect the mass of electron will be negligible compared to mass of neutron. Suppose if the mass of revolving particle, if it is not negligible, if it's comparable to the nucleus, then both the nucleus and the revolving particle, revolving negative charge particle, they'll be moving above the common center, where we can write M1R1 equal to M2R2, then R equal to R1 plus R2. Solving this, we'll get R1 as, then here we'll get the R1, R2 individual, we can find out the values. Then the reduced mass will come. What is the reduced mass? Where mu will become reduced mass of system. So how much mu will be? M1, M2 by M1 plus M2. This is the value of mu. So if you go and check the mass of the system, will be less than the sum of mass of the total particles of the nucleus plus that of the revolving particle. This can be some mu metric atom where the revolving particle will have charge of electron, but its mass will be 702 times that of electron. Definitely we cannot neglect the mass of revolving particle. In that case, the nucleus, which is the proton, and the muon will be revolving about the common center. Then these are the formulas what we can write. Radius of the nth Bohr orbit equal to m square a naught by z, mass of electron by mu, and the energy in the nth orbit was given by 13.6 electron volt z square by m square, where mu by me, where mu will become reduced mass. So this revolving particle mass I'll be knowing in terms of electron. Even this mass of the nucleus also I'll express in terms of electron, so that we can get the mu. Then I'll substitute, I'll get the radius as well as the energy in the nth orbiter. Same, both postulates will be valid here. Reduced mass concept. Here, what is the angular momentum? Angular momentum will be moment of inertia of the system. Moment of inertia of this system will become mu r square. What is r? R is this one. Sum of these two, r1 plus r2, which is equal to how much? I equal to mu r square. This is the moment of inertia of the system. Like this, we'll define the moment of inertia of the system. I equal to mu r square, where mu is reduced mass here. These are the formulas which you have to remember. What are the few examples like a muon, mu metric atom, Where these are the examples of this reduced mass concept. Asking anything like this in the JEE means very remote. Only for advanced this will be useful, and you have to remember these formulas. Nothing more than this needed. Directly you have to start formula in exam. You can't derive all these things. I'm making things clearer. You have to memorize. There's no other choice. There's an atom. It is moving with a speed u. If it and gets de-excited, de-excitation occurs. De-excitation occurs. Then what conditions will arise, we'll discuss here. So an atom is moving with a speed u. If it de-excites and it emits photon in the direction of motion. So what is the frequency of emitted photon? F equal to F naught 1 plus u by c. What is the initial velocity of the atom? C, the speed of light. F naught is the frequency of the photon emitted when the atom doesn't recoils due to de-excitation. Here also de-excitation will occur. Then if it emits photon opposite to its direction of motion, then the frequency of emitted photon, this F, will be F naught 1 minus u by c. If an atom is moving and if it emits photon opposite to its direction of motion, then the frequency of emitted photon will be equal to that of F naught. What is F naught? When the atom undergoes de-excitation, it will not recoil. Then that particular F naught is what? We have this one. We are comparing with that F naught here. And there's one more data which, if you remember, very, very useful for you. If the electron is revolving in this hydrogen atom, it will have the orbital speed Vn, where the orbital speed Vn equal to c z by 139, and there's a formula for orbital speed, c by 139. This c by 139 is what we'll call v naught, and a naught is the Bose radius, the time period of revolution of this, given by this particular formula. You have to remember this. The time period is proportional to n cube by z square. Then if the electron moves opposite to flow of electron, there will be a current. The current is given by this one. And the current will be proportional to z square by n cube. Then this, when a current I flows, definitely like a current carrying ring, it will produce magnetic field at the center of the nucleus, and that is proportional to this one. So the current, which will be proportional to z square by n cube, the magnetic field will be proportional to z cube by n to power of 5. Then we can also define the dipole moment. Magnetic dipole moment, which is given by m, which is equal to current into pi r square. Current will be proportional to how much it is. This is something a z square by n cube. Pi radius will be proportional to b n to power of 4 by z square. This will be proportional to, say, some d n. So the dipole moment will be directly proportional to the orbit. D will be all the constants. Like this in exam, you should magnetic dipole moment. There's a formula. So this should be proportional to n. Mag field proportional to z cube by n phi. Time period proportional to this one. Reciprocal of this will be the frequency. What is the frequency? Frequency will be proportional to z square by n cube. These are all the basic formulas. Very important, you have to remember, that's all, nothing is there. If the electron de-excites, then definitely any torque will act on the atom. Yes, there will be torque will be acting. Or we define the torque equal to change in angular momentum by time taken. What is the change in angular momentum? mv higher orbit. So angular momentum in higher orbit, this will be mvn rn or mv2 r2, or this equal to n2 h by 2 pi minus n1 h by 2 pi, h by 2 pi n2 minus n1, 2 minus 1, which is equal to h by 2 pi. So this will be the torque. This everything should be equal to by delta t. Or this will be h by 2 pi delta. Delta t is the time taken by the hydrogen atom to jump from higher state to the lower state. This will be the torque acting on the atom. Small idea, sir. We'll give delta t. If it jumps from n equal to 2 to 1, there's a formula. If it n equal to 3 to 1, then 3 minus 1. Here it is making excitation from 2 to 1. 3 to 1, 3 minus 1. 4 to 2, 4 minus 2. Small idea based question, sir. Very, very important. We have hypothetical hydrogen atom with the potential energy of the atom varies with the radius r. Then A and B are constant. Then we have to calculate the radius of the nth Bohr orbit and energy of the Bohr orbit. We know F equal to minus du by dr. Differentiating this, minus A by r. Okay, B is a constant. Log derivative of log r will be 1 by r, so A by r. This will provide required centripetal force mv square equal to A by r, or V equal to A by m. This is the expression for speed. Then we know angular momentum, Bohr's postulates. V we know root of am nh by 2 pi. So where this r will become equal to nh 2 pi root m root am. This is the expression for radius of the nth Bohr orbit. Then what is the total? We need kinetic energy here. The total energy will be sum of potential plus kinetic. Potential energy is given by A log nh 2 pi root am. Kinetic energy half mv square. So this will become A log nh 2 pi root am plus A by 2. There is energy in the nth orbit. Like this, a revolving like this, we can construct an hydrogen atom will be of where the potential energy will not be just proportional to 1 by r, proportional to log r. We have the hypothetical like an atomic structure where the magnetic field and the electron will make the matter, will become the atom. Then will provide required centripetal force. This will be velocity. So the magnetic attractive force between them will provide required centripetal force. So Fb equal to mv square r. We know this equal to qvb, where q is the charge of electron, m is the mass of electron, b is the magnetic field, equal to mv square r, where qb equal to mv by r, and mvr equal to nh by 2 pi. mv r will be mv by qb. So this will become v square equal to nh qb 2 pi m square. This will be the speed, orbital speed. Then how to calculate this v? So v will be nh qb by 2 pi mr square. Substitute this here, we'll get the expression for radius of nth Bohr orbit, nh by 2 pi mv. Substitute this v here, we'll get the radius. What about the energy? Already we know kinetic energy, potential energy, interaction potential here. This electron, opposite to this, flow of current will be there. Then this will be like a dipole moment. This will be minus mb cos theta. What is m? Dipole moment, cos 180. Then this will become cos 180 minus 1 minus of plus will be current I into pi r square b. Then what is I? I is equal to charge by time period. Time period is given by 2 pi r by v. We know r and v. We'll get the current, r square we know the man field we'll get, and the total energy will be sum of potential plus kinetic. Like this, we can have atomic structure where a magnetic field and revolving charge particle will make up that atom. Possible. We can have another system where two particles, one particle enters, other particle will revolve around about under the action of gravitational force. Even this will also make as it has a one atomic structure. Then will power required centripetal force, the gravitational force, mv square r. This should be equal to g m naught r square are equal to b square. Then Bohr's postulates, mvr equal to nh by 2 pi. Substituting the mass of the particle is m, v as it is, r will be gm naught by v square equal to nh by 2 pi, where v is equal to gm m naught 2 pi gm m naught by nh. Substitute the v here, we'll get the radius of the Bohr's orbit. Then what about the energy? It will have two forms of energy, kinetic energy plus interaction potential energy. Interaction potential energy is given by gm m naught into r. We know v, we know r. Substitute, we'll get the radius of the nth Bohr orbit. This will become nucleus. Sir, what about the charge? We can have atomic structure where there won't be any charge. This is called hypothetical Bohr's atomic model. Very important. Possibility of asking. You have to be extra careful. Very simple. Can be asked in JEE mains. Next we have the X-ray Schooley's tube. This will be a glass chamber. This will be the target atom. Z. This will be the fast moving electrons. Here we apply the tube voltage, and this will be the accelerating voltage. So first here current I will flow. Means here from here the electrons will flow. These electrons when flowing will generate heat. Due to it, thermionic emission occurs. Then these electrons will get generated here. Now the electrostatic field present here. Who will produce this field? The tube voltage. This will be of order 20 kilovolt to 100 kilo. Very high voltage. So very high electric field. These electrostatic field will accelerate it. The fast moving electrons, they strike the target atom. They lose their kinetic energy in the form of EM wave. Once the kinetic energy 0, will be attracted by the positive terminal of the voltage, and again the electrons will be emitted. Now how many electrons it has lost, it will get back here. From here the electrons which will flow here, which is lost, it will get back here. So like this here, this will be a accelerating, this will be the accelerating voltage. This is called as, what is UA? UA is called as accelerating voltage. This is called like a tube voltage. What is tube voltage? This will be of order few, like a 5 to 20 volt. This will be flow of current. Okay, this will be the flow of current will take place in this way. Okay, now first here the electrons, the current I will flow. It will be generated, thermionic culture, the electrons will be ejected. These electrons will be accelerated by this high voltage connected here. The fast moving electrons, when they strike the metal, they lose their kinetic energy in the form of EM wave. And that particular EM waves, what generated is called as a X-rays here. That's a basic idea. Since only like a 2% of the kinetic energy of electrons will be converted into X-ray, the remaining will be converted as heat. To take out this heat, we'll send the water here. Water will be circulated. To cool the target, we'll circulate the water. So this will determine the speed of electron. This will determine the amount of electrons. How much of current. Means by varying this tube voltage, sorry, this is accelerating, or it is also called as a tube voltage. We'll call this as filament voltage. This will control the number of electrons emitted by this coil, and this will control the speed of electrons. I'll write it here. Controls the number of electrons emitted. What about this? This will control the speed of electrons. And this is the target. This is the water will circulate here. And this is called like a coil, filament coil. And this is a simple diagram. Just remember it. Very, very important. Within another 2 minutes, I'll finish off this. Okay, this now when that fast moving electrons, accelerated electrons here, when they enter into the target material, they'll encounter collision. With what it will encounter collision? With the material itself. Continuously it will lose its energy. 95% of energy will be lost as it. Only 5% will be converted into electromagnetic wave, that is called as X-rays. When that electron passes through the material, so its kinetic energy decreases. The decrease in kinetic energy will be converted into the electromagnetic wave. That particular electromagnetic wave, we'll call that as X-ray or X-rays here. Then why will all have same wavelength? No, definitely when it is moving, it will lose continuously kinetic energy. Suppose it is having the 50 electron volt, it will become 45, it will become 40, it will become 35, 32, like this continuously. The kinetic energy of electron decreases, continuously it will be giving out the photons, and that X-ray photons will have all the wavelength, and that will lead to the continuous spectrum. Here we are having here. And for that everything we are having some sort of a threshold. We are having a threshold wavelength. So there won't be this minimum wavelength. Next we have there's a continuous spectrum. Why does this continuous spectrum? Because the electron, when it's passing through the target atom, target material, continuously it loses out its energy. 95% lost as it, the remaining 5% which will be converting to EM wave, its spectrum will be like this, the intensity. Then there is one particular like a electron which will lose all its energy in the form of the EM wave, in the form of X-ray photon only. And that particular electron, it will get accelerated, then accelerating potentially into V naught, and the whole kinetic energy of that will be converted into X-ray photon, SC by lambda, the cutoff wavelength. This is called like a lambda minimum. We'll call this as cutoff wavelength. So what is the condition for this? The whole kinetic energy of the accelerated electron will be converted into X-ray photon. What about these particular electrons? Only a part of that will be converted into X-ray photon. The curve will be of this kind. There won't be any photons whose wavelength will be less than this. This is what happens with the continuous spectrum here we are discussing. Then as you vary the accelerating potential, the peak of the curve will increase and the cutoff wavelength will decrease, because as you increase accelerating potential, cutoff wavelength will decrease. A simple idea. Next we have the line spectrum. We'll be discussing the line spectrum. The fast moving electron, when it is moving, it will knock out the innermost valence electron here. Then there will be vacancy created in K shell. To fill up that vacancy, so here what we get is like a electron from L shell will jump to the K shell. Like that we'll get lambda K alpha. Then if the vacancy is there in K shell, if filled up by M shell, then we'll get the lambda K beta. Okay, fine. So now why the line spectrum? When the fast moving electron continue, it will be generating the continuous spectrum will be there. Along with it, if it knocks out the innermost valence electron, here it will be there. A vacancy will be created. This vacancy will be filled up by the electron in the L shell, and this will be ejected electron. And this will be scattered electron. Means the fast moving electron, here it is, it comes, collides with the valence electron in the innermost shell K shell, it will create vacancy. This is ejected. This vacancy created will be filled by the outermost orbit. So here we'll get a photon. This will become lambda K alpha, lambda K beta. Based on that, so here it should be lambda K alpha. That lambda K alpha, we are plotting it here. Lambda K beta. Then if there is a vacancy is there in the L shell, then it will be filled up by M and N higher orbit. Then we'll get L alpha, L beta. Then we'll get even K gamma also. Here L gamma. Then as we increase the voltages, K alpha, K beta, their wavelength will not change. Okay, fine, this one. So here what is the observation? Lambda K gamma less than lambda K beta less than lambda K alpha. Why the intensity curve of the K alpha will be more than that of K beta? Because if the vacancy is there in the K shell, the probability to fill the vacancy in K shell will be more due to L than or N. That's why the intensity of K alpha will be more than K beta. Why lambda K alpha greater than lambda K beta? You look at the transition. If there is a transition from L to K, we'll get a photon lambda K alpha. If the transition from M to K, we'll get a photon, which will have more energetic photon, M to K. If the energy is more, wavelength should be less. So lambda K beta less than lambda K alpha. This is a line spectrum. This particular wavelength depends upon the value of Z of the nucleus. That's why it is called as a characteristic spectrum. The wavelength lambda K alpha, lambda K beta depends upon the Z of the target atom. That's why they're called as. So this is like K alpha, K beta. These are the curves. Here we'll get the K gamma. This is a continuous, this is a line spectrum. Next we are having the Moseley's law. So here, so what this law says is that the wavelength of this particular thing means the K alpha, K beta. Now the periodic table, it was being classified based on this Moseley's law. What Moseley's law? The square root of frequency of the photon emitted due to de-excitation is proportional to Z. It will not pass through the origin, it will have some intercept. So based on this, what happens in the periodic table, the elements are being classified here. Now when the electron, if there is a vacancy in the K shell, okay, there is a vacancy here. We'll fill up this vacancy from the L shell. Let's assume that there is a vacancy is there, where the vacancy is brought here. Now why this vacancy has come? Because the accelerating electron will knock out this. Here a vacancy is set up. This vacancy I'll indicate by yellow color. We'll fill up this vacancy by outermost orbit. Here if it is filled up by this electron, then it will emit lambda K alpha. If this electron makes a transition, then we'll get lambda k alpha. If this electron makes a transition, then we'll get lambda k beta. Like this, we can use this particular formula. The difference in energy, that one. So here, why z minus 1? Because when this electron making transition along with the nucleus, it will see this electron. That's why z minus 1 is brought here. Similarly, h fk beta should be equal to mass of electron, charge of electron, 8h square epsilon naught square z minus. When electron is making transition here, what is the net charge it will see? It will see z minus 9 whole square, and it will make transition 1 minus 3 square. Fk beta. Like this, solve for Fk beta. Then if you want lambda, because what is F equal to? H by lambda. This will become where Fk beta equal to H by lambda k beta. Then we'll get expression for lambda k beta. Why z minus 1? Because when this electron making transition, it will see this 8 electron plus this 1 electron, z minus 9. Similarly, H F L alpha, if there is a vacancy is there here and will be filled up by this, then they should become equal to MEQE to the power of 4 by 8 H square F naught square. What is the net charge? The M will see, it will see it as here 2 electrons, here 7, Z minus 9. If there's a vacancy is there, if the vacancy is present here 2 electrons, here out of 8, 1 vacancy is there, Z minus 9. Then this will become 2 square, 3 square. Solve for this, we'll get FL alpha. Then FL beta. Like this we can calculate. This is about the Moseley's law, and these are the type of questions can be asked. Better directly you remember this formula. A and B will be different for this one. So we are discussing this for Fk alpha. For generalization, this values are for lambda k alpha. For different lambda k beta, lambda k gamma, this will be different. This is about the Moseley's law. Then we'll come back to the X-rays. So in the X-rays, the intensity of X-ray, we'll take the continuous spectrum. This particular intensity of X-rays, the intensity of X-rays depends on what? Depends on accelerating voltage, and depends also on the target material, the value of Z. As we increase the accelerating potential, the intensity will increase. Next again, the penetrating power of the X-rays. The penetrating power of X-rays depends on accelerating voltage. By increasing filament current also, we can increase the intensity of X-rays. These are all basic things which you have to remember. Very small topic, just general formulas are there, try to remember. So only thing is, 2 wavelengths are there. One, cutoff wavelength. Cutoff wavelength depends on accelerating potential. Lambda k alpha, lambda k beta depends upon the Bose atomic model. This method, Fk beta, lambda k alpha, lambda k beta, these are the methods you have to follow it. Okay. Okay, kids, we have discussed about the atomic physics and X-ray one shot. Almost all the ideas I covered it. It is coming around 1 hour 40 minutes. If you watch it, almost all the basic fundamental concepts you are going to understand. Then remember the formula, solve PYQ will be a far better question. So we have discussed the basic earlier atomic structures like Thomson's atomic model, Rutherford atomic model, then Rutherford alpha scattering experiment. Then we entered into Bose model, Bose postulate. Then in the Bose postulate, how to find out the radius of the nth Bohr orbit, speed of the nth Bohr orbit, energy of the nth Bohr orbit, then hydrogen spectrum, then how that hydrogen spectrum is a line spectrum. Then we discuss the excitation and de-excitation of atom. What do you mean by Rydberg constant? Then binding energy and ionization potential. Then we discuss the excitation of hydrogen atom. This is a central part of the your entire atomic physics. How the hydrogen atom will get excited, or any hydrogen or like atom when they get excited. We can excite by photon, or by electron, or by some incident particle like a proton, neutron, or hydrogen atom, or hydrogen like atoms, or alpha particle. Then some based on this, some collision based some questions we have discussed. Then we came to the recoil speed. If de-excitation occurs, the atom will not be at rest, will be moving. Then we discussed the reduced mass concept. If the revolving particle is having a mass, then both the revolving particle nucleus they revolve about the common center. Then we discussed the hypothetical hydrogen-like atoms. Atom means doesn't mean that electron and proton. It can be made up of anything like electron magnetic field. Then like a two particles each of mass m1 m2. Then mu meson. It can be anything that one. Like this, there's a hypothetical hydrogen-like atoms. Then we discussed X-rays, continuous spectrum, line spectrum, then the particular cutoff wavelength, then lambda k alpha, lambda k beta, Moseley's law, all the applications we have discussed. So these are all things will happen in atomic physics. So you have to really go through it all this one now. If you understand these concepts, then remember formula, then you will be in a better position to deal with the questions in exam. Unless you don't have this much of clarity, not possible in exam. Okay, fine. It's just 1.5 hour. Go through 2-3 times. You'll get exact basic picture. Then remember formula. Solve PYQ. You'll gain confidence. Okay, kids. Thank you. Thank you very much for your great support. I'll end up the session. Okay, take care all of you.